All right. Good morning, everyone. So, team have set the scene beautifully. How wonderful is the opportunities are of molecules, and I guess today we're going to now to reality. What the experimental challenges really are. Okay, so just to briefly recap, I mean, what we've spoken about so far is we have a lecture on getting into the weakly bound state, and a lecture on getting to the ground state. And I told you about the horrible, messy collisions that are happening there, causing our molecules to go away. They're still there, but we're just going to ignore it. So if you wonder why I only measure out to maybe 1 second or something, that's because these collisions are still there. So as I said, way back in the beginning, I suppose primarily our interest and opportunities on quantum magnetism and quantum computation. So that's the aim today, is to try and show you how we control the molecule, just as you said, towards realizing some of these models. And I also showed this slide. We also essentially covered, right, this nice quantum magnetism system where we have these spin exchange interactions, direct pricing interactions. And I pointed out it's actually quite hard to do this. And the reason I pointed it out, what I highlighted was this energy scale. So this is the dipole-dipole interaction for rubidium cesium molecules, which have a divide, which standard kind of size dipole in a 1064 nanometer lattice. So the spacing is 5 nanometers. And I highlighted that this is only in kilohertz. This is why kind of always says, yeah, but when you turn on that field, the shit's a megahertz. Right, that's why we worry about turning on these electric fields, because we would have to control them to well below this kind of energy shift. If I can control everything in the experiment, below this kind of energy scale. So that's what we've been working on for many years, how to do this, to really get a handle on all the shifts that are happening in the molecule and be able to control them at a level that it's not true. So the plan today is to, as follows. I'll start by going to the hyperfine structure of the molecule. The glory details of what we really need. It's not just n is 0 and n is 1, right? There's all this hyperfine structure that Tina mentioned earlier in the week. And then how we control state within that hyperfine structure. I'm going to revisit the AC start shift, which I introduced earlier in the week. And then I'm going to show you how, I'm going to show you how this is problematic, and then how we can solve the problems associated with it by engineering the trap in a way to eliminate these excisions. And I put time permitting, but I know Hussein is a very generous man. So I will carry on till the end, because I want to tell you about some of the we're doing in users. It's kind of a completely different experiment. Okay, so I showed you this. This is our steer up to the ground state. And when I showed you this, I said we go to the absolute ground state, the ground state, and I told you to take it one for us. But now I need to show you that that's actually the case. Right? I want to reiterate that what we do always in these experiments is reverse this stirrup, break the molecule apart, and image the atoms. And the stirrup is addressing a single item. Okay, so in a sense, we've got hyperfine state sensitive detection. If we drive the population out of this hyperfine state, it will appear like a molecule. That's the state sensitive detection. So what we're going to do in this talk is retrap the molecules. Remember, I explained the need to turn off the dipole trap in iron. So we retrap them, and then we're going to turn on some microwave and interrogate them. And pretty much everything I'm going to talk about is in a bulk gas. So it's just a 3D optical trap, or maybe not even trap in free space, around 4,000 molecules at a microkelvin. And yes, just to reiterate, those collisions are happening, but we're just ignore. Okay, so I was worried about you to talk about this theory, but Simon's already introduced it. This is we don't deal with the 32 terms from Brown and Carrington. The molecule solves that for us. What we do is use this effect of Hamiltonian diffusions. Here it's solved. Oh, here it's solved. Oh, the molecule.
Credit. Let's give credit where it's due.
Okay. So what we have here is the rotational structure that we like, and but sometimes we have to include this centrifugal distortion term. And then we've got this hyperfine structure that you can talk about and explain. So there's this nuclear electric quadrupole interaction. There's the interaction of the nuclear magnetic moment with the magnetic field due to the rotation of the molecule. There's the spin-spin interaction between the nuclear magnetic moments. And then there's a Zeeman term, there's a rotational Zeeman interaction, and then there's the usual nuclear Zeeman interaction associated with nuclear. And he very nicely, I enjoyed it, guided you through how you might derive the matrix elements or something like that. Actually, this is a kind of advert, but I hope it's a useful tool. And so rather than going away and deriving this book yourself, we actually, one of my students wrote a code to do this in Python, because I know lots of young people like Python. And that's available here. So this will solve the hyperfine rotation for the single signal. So every calculation I show comes out. So I encourage you to use it if it's useful. Do you want to convert it? Well, so that actually, so Jesus, who originally did the calculation for us, has the code in Fortune, and student converted it to Python. I thought it was very nice. Okay, good. Right, actually, I skipped a bit. So let's look at the hyperfine structure in the rotational graphs. Things get a lot simpler there because we can actually drop lots of these terms. And we'd actually just left with this spin-spin interaction with the nuclear Zeeman effect. So this is what the hyperfine structure looks like for the rubidium cesium in the rotational ground state. We have these 32 hyperfine states, which are spanning something like a megahertz or so. Typical magnetic fields. The flow field, Stephen said, the zero field, the spin is coupled, so we can think of a total nuclear spin, and then they're just separated by this constant for having this normal, which for rubidium cesium is about 19 kilohertz. And in high field, everything decouples, and we can just think of things in terms of the nuclear spins due to the Zeeman effect. But everywhere we do our measurements, we're kind of in this medium region. Everything's kind of So to get to the ground state of this hyperfine structure, so what we need to know is actually we're starting out from a flashback state with a total spin projection of first of all, and this is going to be preserved through the theorem. And so we can address different transitions down here in the rotational ground state by controlling the polarization for Dirac layers. So the pump is always parallel to the magnetic field, and then if you change the polarization of the Stokes field, if it's parallel, it can address +4 states. And if it's orthogonal to the magnetic field, we can drive transitions to +3 or +5. Of course, you see +5 is the absolute ground state, the one we'd like to go into. Put the molecule there. It's the ground. So that's what we can do. We can change these polarizations. We can see two resonances in Dirac, and actually, we know from our microwave spectroscopy that these are actually addressing two particular states. This +5 state and this +4 state. So that's how we transfer the molecule down here. This is a really nice starting point for everything that I'm going to show you. Not only is it the absolute lowest state in the molecule, but it's also the fully spin stretch state. So as Tina said, all of our calculations we do in this uncoupled basis. That's the simplest way to think about the state composition of the molecule. And this is nice because it starts out in very nicely well-defined spin structure. Okay, so let's then have a look at n equals 1. Okay. So what we have now is, of course, 3 times as many states, right? Because we've introduced the Mn projection, so we get 2n plus 1 times the states. So here we have 96 hyperfine states. And what we're going to do is drive transitions from this +5 state with microwaves up to here. And just to highlight the transition frequency in rubidium is 9. Big heavy molecule, very small rotation constant. Just as an aside, actually I should credit, so this is the continued advert of the atomic high. You can actually give it to an undergraduate, so this is all the undergraduate students' work, and he's been comparing molecules, searching this internal space to find nice states that we could use to encode units and do things. But this is just to give a fingerprint of the different molecules that we have, right?
Does that calculate the ETM as well?
The dipole mix, yes, yeah, the dipole mix. As a function of magnetic field. So you can see every molecule has a slightly different fingerprint, right? And that's not surprising. Well, first of all, of course, we've got different numbers of nuclear spins, different numbers of states, but of course, these interaction constants are all different. Okay? But these numbers come from this paper by Jeremy. And I guess when I first saw this for sodium cesium, the pattern there, but I think because these coupling constants for the nuclear spins are almost a factor of 2, or the levels sit on top of one and create this quite simple pattern.
Well, I feel like the difference is actually the quadrupole on my beds.
Well, this is n equals 0, so there's no quadrupole interaction. Yeah, but you see these C4 interactions are quite different in magnitude from one molecule. And what that means is getting into the fashion language, varies quite significantly from one molecule. And just, yeah, you can also see the n equals 1 and n equals 2. Compute that in this code, and there you see differences in. That's where the electric quadrupole interaction comes in, the differences there. So here, sodium rubidium, for example, you have this huge splitting compared to, let's say, sodium cesium or sodium potassium.
Yeah, I want to read this 10 times speed resolution. Series of beta.
It's very useful with them. And sodium cesium doesn't have that.
Yeah. Okay, so that's set the scene. What the hyperfine structure looks like. So let's start to manipulate the molecule, try and move around inside this internal place. So although we've got 92 states, n equals 1, of course, selection rules limit that, and actually we can only access potentially 10 states here. So the electric dipole selection rules, of course, are we can only change Mn by 0 plus minus 1. The nuclear spins have to stay the same, or in other words, we can only change this Mn quantum number by 0. So coming from +5, we can address +4, +5, +6. Okay, so when we started this, we expected to see just 10 lines in the microwave spectrum. So the first thing you learn when you start to do this, turn on your microwaves, and those people do this, you will realize that actually that one device is pretty big, compared to if you're used to trying to drive a microwave transition in a handsome by a magnetic dipole. It's very easy to drive fast radios. which is good, that's what we'd like that. And just as a reminder, I put this up here, we're always measuring the number in the absolute hyperfine rotational ground state by return to zero. Okay, so when I apply microwaves, you see the number of molecules go away, but they're not actually being lost, they're just being transferred over to equals 1, where we go to 10. And so to do spectroscopy, what we do is try and engineer something approximating a high force transfer of 10 equals 1 the spectrum. And that's what we observed. So we've looked for these individual lines, although they're close together. The microwave spectroscopy is high resolution. In fact, each of these lines is just limited by the duration of the force that we use. There's no decay from the technical rotation, so from a sensible lifetime scale. Okay. These vertical lines are what we do. We fit that Hamiltonian to it to really pin down the constants of the molecule. And we repeated that at another magnetic field. That's just showing me each one of these dots is a separate measurement of that type of spectrum that actually helps us identify which transition is which. And out of this, as I said, we get these constants that model very accurately. That kind of completes the map. You'll notice that actually we only measured 8 transitions, not the 10 that I advertised. And these two we did not observe. And actually then, if you solve the Hamiltonian to get the components of this wave function in n equals 1 that has the correct nuclear spins to couple to the ground state, you'll notice that these two have very, very small amplitude. We squared that to get the transition dipole to these states, but it's just fine. So we can't drive to these particular states at this magnetic field. Okay, that's why they're absent. So,
Sorry, is that because the microwave power is not strong enough?
well, the problem is that you turn up the microwave power to try and drive them, you just start off resonant and put them to the neighboring state, which are much stronger. Right? So it's very hard to drive to these at this particular point. And she just operates. So again, I have to credit Tom. So he came up with this way of showing it, right? So this is actually showing the state composition of those 10 excited states in n equals 1 as a function of magnetic field. So let me talk you through what these colorful diagrams represent. So this gold or yellowy bit is the one with the correct nuclear spins. So this, for example, shows you how the coupling to this particular state changes as a function of magnetic field. Becomes much stronger at higher magnetic field. And then these other colored lines are the composition of other nuclear spin projections in the open basis in this excited n equals 1 state. Okay. So you can see that the problem I was highlighting was these two guys, this vertical line, I think should sit at where we're doing this measurement, 181 Gauss, and these two states have no gold or yellow bits at this particular peak, so we can't really drive transitions to those. The other thing you take away from this is that actually, of course, if you turn up the field, right, eventually you decouple everything, and we should just be left with 3 states. And then equals 0 plus and minus 1 projections. And that's what you see. I mean, this is only going up to 400 Gauss, but by the time you have 400 Gauss, obviously you've got the spin stress state, but then these two transitions are now dominating in composition, and all of the others are tending to 0. So it's a nice way to visualize what's happening through this intermediate field regime in terms of these state compositions and how well we can drive the transition. All of that. Okay. So then you can start playing the games, right? And this is more in the direction of what Timo is proposing, right? So we did this spectroscopy to get the map of the model. Have the code, we have the constants, now we can actually map out all these transitions very accurately. And so we can start to play games. Okay, so the first thing we can do is we can change the nuclear spin stack in. So we can drive a transition up to this +4 state, and this is the composition in this sort of couple basis. And so because we're coming from this stretch state, we're coupling to this part of the wave. Then we can use the other part of the wave function, different spin projections, to couple down with a pi transition back down to the ground. So this is using this nuclear electric quadrupole interaction in N equals 1, which is fixing states, and it's using it to benefit to drive back down and effectively flip a nuclear spin in the ground state. And this is demonstrated before us in ARB. So this is what it looks like. You can drive Rabi oscillations on this transition, and then you can measure Rabi oscillations going down on this transition by sandwiching it between two pi pulses. Okay. Remember, we always have to go back to this +5 state. That's the one that we measure from. And so in order to measure Rabi oscillations on this, we transfer the population up, do some pulse here, and whatever population is left here, we transfer back down and read it out. Okay, that's why we do this sandwiching, this pulse between two particles. Okay, so in this case, we've basically flipped the nuclear spin between these two states. I'll show you later how we use this to store quantum information in the model. We can also go up the ladder, rotational states. Okay, so this is just driving up this stretched ladder of states. And the satisfying thing about this was this dashed line was predicted from the model based upon the spectroscopy. Okay, so I just wanted to highlight this, that actually once you've done this spectroscopy carefully, you can just dial in whatever transitions you want within the model and address particular states. Okay. And in fact, we didn't stop there. We went all the way up to N equals 6, which was actually when we ran out of pi-point sources. I mean, this is the spectroscopy going up to N equals 6, and then this is showing Rabi oscillations on, I think, the 5 to 6 transition. Okay, so we do pi-pulse, Rabi oscillations, and then pi-pulse, back down in order to read out. Okay, but you can do that, right? It's just microwaves. It works. And Jake, student, made this very nice picture. What we're doing, right? Going up this rotation ladder, cesium model. And I mentioned, you know, I'm quite interested in encoding synthetic dimensions in this, using this thermal state, internal space, and some. And that's the direction we're taking. So we're going to talk a lot about engineering coherence, and Tina's already explained to you what that means and what we have to find, and it essentially is the basis because of different molecules experience in different shifts for whatever reason. And the standard sequence we use is a very simple Ramsey sequence. Okay, we do a pi/2 pulse, prepare a superposition, 2 states, then we wait a certain amount of time and interrogate that superposition with another pi/2 pulse. I do this Ramsey spectrometry. And you can do that. This is all in free space. Okay, so we can do that, and you can vary the frequency of your microwave pulses, and you get these standard Ramsey fringes, and actually measure these transitions to a few hertz this way. But again, really do know what the interactions and shifts are in this molecule. And we can also vary the time. Okay. We can fix the frequency of the pulses and vary the time. And this is what we see. And this is in, I should emphasize, the no track. Okay, so what we see here, there's no loss of coherence, but this is only out to 2 milliseconds. But we still have full contrast fringes, but the signal's going. Okay, and all that's happening is our molecules are expanding and falling, and our little stirrup beams that transfer them back are not big enough. Okay, so eventually they drop out of the stirrup beam, and we don't see anymore. And in fact, this line is measured independently. This is just measuring the number of molecules. You just let them fall through space. Okay, so So the obvious answer is just track your molecules, right? Right, don't let them fall, just track them. Steady, and it's only taken us like 3 years to figure out how to do this in a way that preserves this coherence. That's it. So, any questions at this stage?
So I think you distinguish like in terms of dephasing, like maybe it's useful to talk about homogeneous versus T2 star versus T2. Do you find it useful to make that distinction in your experiments?
Yeah, I think most of what we measure is due to inhomogeneous potential. The molecules standing different.
So you can do just in echo it.
Yes, yeah. Yes, to some degree. Yeah. Yeah. So, but what we'd like to do, and what I'll show you is, we want to learn how to not have to do spin echo, but actually learn the conditions that we can actually engineer really long programs without.
Like whenever you said you went with that ladder, I think 6 drones.
Yeah.
How many losses, like, were the losses due to radiated lifetime loss? Like, just, like, should we have on and spontaneously emitting with those losses coming out?
There's no spontaneous decay involved. Okay. These, the lifetimes of all of these rotations take basically.
You're doing these measurements in the state and show that it already existed for more than 5.5 seconds. 5%.
So the loss is all collision. Right. There's no radiated decay because they're all microwave transitions. So they've got lifetimes and black body doesn't even affect what it is. So effectively, think of all of those levels on the time scale of the experiment.
Or it is one. It's not, it's very old.
It's, yeah, the lifetime of the I think I can't remember them, but it's tens of thousands of seconds. The like the black body.
It's not limited by spontaneous.
No, it's one day is the 4 gigahertz.
What's the microwave transfer efficiency?
It's as close to as 100% as we can measure within the noise of the molecule.
Or every.
For every level. Yeah, it's just limited by how well we can resolve the number of molecules. I'll show you more Rabi oscillation data. Do a Rabi oscillation in 7.5 volts based on and within the noise, it's
Can you maybe make a few remarks about scalability? We have this spaghetti of states in the ground state, in the excited state, etc. We have maybe a long chain or a wave of molecules. They all coupled by light interaction, which is long range, so all the levels are kind of shifted and split and whatever.
Yeah.
So
well, that would be the key.
some of the normal light types, for example, their scalability is an issue. And their qubits are kind of well defined.
Yeah.
In the sense that the states are less than void. In case maybe the molecule is not so much. So
Yeah, so I think I mean the direction we're going at the end is very similar to Cancun. It's well, we have 2 experiments. One to try and put the molecules into a lattice. But really we'd like to have a single site addressability. So we also have this experiment on assembling molecule tweezers. And I don't know what the atomic state of the art is now in Mishra's lab. I guess that's a place to ask, but I guess it's pushing like 1,000 atoms in tweezers. I'm not going to say we get 1,000 molecules using this assembly technique, but I think you could believe that you can make hundreds of molecules in individual tweezers with individual addressing. Yeah.
and still with all of them in a reasonably time scale.
I think so. Yeah, I think I'll show you that we can get a handle on everything that we need to. The light chips are big enough to take molecules on and off resonance with microwaves. So I think it should be possible to control the light chips and address individual molecules in the ensemble. Of course, there's a lot of work to do that, but I don't see a physics limitation as such. There are lots of technical challenges, but not so much of physics. Okay, let me carry on. So talking about trapping, we're going to revisit the spark chips that I mentioned, the AC spark chips. And several others have spoken about this week, and you know, the understanding that we have this anisotropic polarizability. So in general, this alpha parallel along the axis of the molecule is much stronger than this perpendicular component of the polarizability. Okay. As I said, we often write it like this way in terms of an isotropic polarizability and this anisotropic. This is good, as I stressed. Contributes to trapping for all rotational levels. It's the same for all rotational levels. This is not so good. It's almost zero for n equals 0, but different rotational states, it mixes the NF projections. What that does then is change the transition frequency in the molecule. These micro transition frequencies. And so these are the matrix elements if you write out this interaction in the n basis. And you see it has these diagonal terms with this P2 cos beta form, but it also has these off diagonal terms. Okay, so it really fixes everything up. And this is in the n basis. Remember, we've got hyperfine structure that's already mixed in, okay, on top of that. Okay, so this is a really complicated problem. So this is what it does, right? To the spectrum. Okay, so what we're looking at here is the microwave transition frequency. Now, as a function of the intensity of the trap, okay, so we're retrapping molecules and measuring those transitions as a function of the laser intensity. And each one of these little dots is one of those little spectroscopic measurements as a function of intensity. Okay, and what's shown in this blue and red are different microwave polarizations. So the blue, it's said that's along the quantization axis, and red is along the quantization axis. And what you can see is this spaghetti elements. The transition strength is coming, going, the states are bending over. It's all quite complicated, but I should say, you know, the lines are the theory. So although it's complicated, we totally understand it. We can totally model it. Right? So it's just hope that we can learn how to control it. And I should point out this is the polarization of the laser with respect to the magnetic field. So this is orthogonal to magnetic. Polarization matters. And just to point out, this is what Ken was talking about yesterday, that actually if you crank up the intensity, then eventually the laser wins. Right? And the molecule says, forget the magnetic field, I'm just going to follow you. And all of these states become linear, just with the intensity. But we don't want to go that far. We want to be somewhere in here, where we have all these lovely avoided crossings. So we can change the polarization. As you'd expect, if you put the laser polarization along the quantization method, things get a lot simpler because you're not fighting two different interactions so much, but there are still avoided crossings and there are still big shifts. And it's very sensitive to the angle. So this is a zoom in of this little corner down here. And this is at 90 degrees for the laser polarization, and this is 10 degrees. Well, we open up this big avoided crossing. I often tell the story. This is a challenge anybody who's come up with a more expensive way to measure your laser polarization than this. Because this is what we measured, and we kept saying to Jeremy, no, we're measuring this, and he said, no, it should look like this. And eventually we went back to the lab and the laser polarization was 10 degrees. After the year. Sorry. Here. Yeah, yeah. And actually, this is another summer student using diatomic light. This is a nice movie we made, right? So this is looking at those transitions now, and what we're doing is just changing the laser polarization. Much interesting. And that helps you visualize the spaghetti of states that's happening here, and how they all change in this laser polarization. It's a lot of fun, as you can see. But you'll notice in there are regions where it looks pretty flat. And for the experimentalists, get excited about it, right? Because if the transition is no longer sensitive to density, that looks good. And okay, so that's actually what we did. This was quite a long time ago. So we did a Ramsey sequence in the track comparing these two states. This one, it just has this linear shift, and we see this very rapid dephasing. And this one, which has this avoided crossing, and in principle should allow a much longer coherence time. And it is much longer, but not long enough for what we want to do. It's under fast dephasing. We can map that out as a function of the intensity, and this line is just essentially a gradient of this curve. Sure enough, we see a peak at the avoided crossing. But let me go back, sorry. But we're only achieving coherence times of about 0.8 milliseconds. Yeah.
Maybe a technical question, just out of curiosity. These look like very high intensity numbers. What does this laser look like? Power and
Actually, they're not very high intensity numbers. So that was the problem with this. So we normally, so we normally track around here. And so for the mean waste that we have in our experiment, that produces around the 10 microcolor heat track. And so one of the problems of this experiment is the avoided crossing is actually too low in intensity. So the molecules don't remain fine, they drop. Yeah.
So the typical intensity you try is just big things. Is it much higher or much lower?
So usually we operate about the upper limit on this plot. That's CV up to price. Yeah. Okay. So the take-home message from this anisotropic polarizability is, generally you've got very strong intensity dependence to these transitions, and if you do this in an inhomogeneous system, then you're going to have lots of all your molecules are going to be evolving at different rates, and eventually they're going to depend. Right? And sometimes you can use SID echo, it depends on how long the coherence is and how much of the information they're actually tackled. But in general, we'd like to eliminate this. And I want to emphasize again that this is due to this anisotropic polarizability, which is just the difference between these two alpha parallel and alpha parallel. So, and this problem should be eliminated at n equals 0. Because we don't have this almost. So let's look at an n equals 0. So nuclear spin superposition in this system. Okay. And actually, I'm not going to belabor this. We've talked about these. There have been many nice proposals and Tanquen's talked about their proposal and talked you through it. And the idea is you store information in these nuclear spins and then turn on interactions by going at n equals 1, do some kind of gate in this system. And we've also had some papers on this, and a paper where we wanted to use many of these ground state nuclear spins to encode a few digits. So we thought it would be interesting to actually understand what really limits the coherence on what we get on this nuclear spin system. Okay. So we started doing some experiments, and we were a little bit naive, I have to say, to start with. So we'd already identified how to transfer between these two states. That's the ones I've showed you. So we did the microwave transfer. We can either do that in 2 steps or is it G2, 2-photon radio oscillation to transfer population between these 2 nuclear spins. And as I said, we should expect non-coherence. Firstly, we only have nuclear magnetic moment. Actually, when we started the experiment, we believed that the polarizability should be identical. We didn't think we would have any instances on it. And in MIT, Martin's Virline's group, they'd already shown that you could get about 0.7 seconds coherence using sodium potassium. So we did this measurement, we did the Ramsey in the trap, and we got like 60 milliseconds. Actually, it's pretty easy to work out what we're doing. So what this plot is showing, so this is the Zeeman plot again, of these transitions. But now what we're extracting is the magnetic moments of the second, right? Just the slope of these. Okay. And we've used these 2 states, okay, to do this measurement. And although we've rushed the nuclear spins under the carpet, saying, oh, they're small, actually the difference is about almost 2 nuclear magnetons, which to get 100 millisecond coherence time requires 7 milligauss stability. We just didn't have it. So actually, this measurement is purely limited by the fact that we use this magnetic coherence. Okay. And then you look at this diagram and say, well, hang on a minute, I use these 2 states. Here, they've got identical magnetic moment, right? So I shouldn't totally eliminate any magnetic decoherence. Right? So that's what we did. So you just change your microwave sequence and use those 2 states, and you go to this field of 154.5 Gauss, and instantly we get coherence times. Okay. So this is measuring that Ramsey sequence, and this is looking at the function of time. The decay, that's those pesky collisions that I mentioned, are always there, causing our molecules to go away. But what we care about is this fringe contrast. And we can map this out around this avoided crossing. So that's this crossing rather. So this is a zoom in of those magnetic moments as a function of magnetic field. And we can look at the coherence time we get, and of course, it peaks right here. And this is just another way of expressing that as a function of the differential magnetic moment. And this all makes sense. Right? It fits to like 30 milligauss noise in the experiment, which is why that first measurement was constant. And you get a maximum coherence time of about. So no surprise in there. That's just understanding what we're doing a bit better. And then could always, the experiment you ask, okay, so what's limiting me now? Why did it 7? And this is where we were surprised by the answer. Turns out you gave the answer. What you said this electric quadrupole interaction mix of n equals 0 and n equals 2. So even n equals 0 is not pure. And that's exactly what we discovered, right? So this is a graphical representation of some matrix elements, right? And what we're looking at is this is basically increasing n. So this is n equals 0, the first 32 states, and then n equals 1, next 96 states, and then n equals 2, the next however many states, right? And we're coloring in some interactions. This top one is this nuclear electric protocol interaction, and this is what Tima mentioned in the beginning. Right? But actually, there is matrix elements that mix n equals 0 and n equals 2. But n equals 2 has an AC, has a propagation right? And this is the AC spark shift that also has matrix elements that are mixing n equals 0 and n equals 2. So these things could combine, and actually they give us a very small tensor line shift in the ground state. That's why I changed saying, the anisotropic polarizability in the ground state 0 to almost 0. Right? And almost is actually a few parts in 10 to the 5. So the mixing is very, very small, but it's there. And you can see it if you eliminate the magnetic field. And so this shows that we can measure that, right? So this is now measuring, doing this Ramsey sequence, measuring the 2-photon detuning that we have in the experiment. For the laser beam polarized parallel to the field and perpendicular to the field. And I should emphasize these shifts are on the order of tens of terms. Tiny little shifts, but measurable with the Ramsey. And we can measure it as a function of the angle, so it's shown here. And it shows the standard P2 cos theta form that we expect from anisotropic polarized curve. This is the free space value, and I'm sure many of you know that this has a simple magic angle of like 54.7 degrees. So the answer is just set the laser polarization to the magic angle, and then you get no shift. Eliminate this anisotropic tensor line shift in the ground state. So we put all that together, we have the right magnetic field, the right polarization angle, and then we do the experiment and we measure the coherence, and we push out as long as we can, which is just 1.2 seconds. Those pesky collisions are still getting things, right? But you notice the fringes here still full contrast. There's no loss of coherence after 1.2 seconds. And actually, we didn't even know how to analyze this normal error analysis doesn't really work. So that's why in the paper we actually just give a confidence limit. We can only estimate the lower bound of coherence. So with 90% confidence, we can say the coherence is greater than 7 seconds. But we understand all of the shifts, so we can just put in the numbers, right? So if you say, well, I've got 35 milligas of noise, that would actually translate to 2,000 seconds coherence time for these nuclear spins. And if I said, okay, we set the polarization for half a degree, that would give us 80 seconds. And this is I call this on the 5 scale.
Maybe something else will come in.
Yeah, maybe, but I mean, in the first, so of course, what we want to do is put this in the practice, eliminate these testing collisions, and then push this out. Maybe there is an effect.
It's like particle physics.
Yeah, it's this type of error analysis where you only have a one bound in the problem. As it's used a lot in, I think they probably be the end people know about this because it's the same kind of problem. You're measuring a limit rather than actually. We don't get it enough, but yeah. Okay, so this is nice, right? This allows us to store information. Yeah.
So if it's in the lattice, can you achieve this magic angle?
Well, that's a good question. I think there is a way of. It's a little bit complicated, and I think we have a solution. I think it's actually in Dave DeMille's very early paper on this magic angle. I think there's some convoluted.
Like, was it electric beam or?
No, it's some convoluted beam geometry that allows you to do it. Yeah. Okay, so what we really want to do, I mean, the excitement stuff is all in these rotational states of competition. That's the thing that gives the dipole interaction. So what we want to do is extend this from nuclear spins to rotational states. And I'm going to tell you about some work happening today on developing magic traps for the market, rotational magic traps. So this is the problem again. We've got to try and get rid of all of this mixing problem. Okay. So you can ask straight away, well, why didn't you go to this magic angle? And what that magic angle does is set all of these diagonal terms to 0. Right? It doesn't set the off diagonal terms to 0. So if you calculate that for rubidium cetium, right, this magic angle doesn't look any better than it. That's not true of everyone. ARB, the magic angle works really well, but that's basically because you're at high field and decoupled all of the nuclear spins. So you can do the same, you can add an electric field. Right? And that basically shifts all the energy levels, all the orthogonal energy levels far away. And then you get a nice magic angle. Right, but as we've said, we can't really want to have an electric field. But introduces more problems to deal with at this stage. So we want to come up with a different solution. The solution we have is a very simple one. Why don't we just make this alpha 2 0? Right. Just set that to 0, and it goes away, right? And then we're just left with this isotropic polarized form cells.
You still have it. Equal to 0.
Possible. Yeah. But so let's see if we can make this alpha 2 and 0. And I've already shown you how we might do that, because I explained earlier in the week that these alpha parallel and alpha perp actually come from different transitions with the ball. Transitions with different symmetries. So alpha parallel is these transitions to singlet sigma, and alpha perp is to singlet pi states.
I guess that's kind of non-intuitive, I can. The parallel position where there is no projection onto the.
I think that's what we were talking about the other day, explained in Olivier's paper about polarization and projections onto the internuclear axis.
Yeah, but I guess naively, I might think it's the other way around, but.
Yeah. So, so the answer then is just to tune your laser to be close to a transition, right, in the molecule. If you're going to be close to a transition, you can basically affect one of these components without really altering the other. And the transition we choose is this one which is normally forbidden. It's this X to B transition in the molecule at 1146. Okay. And it's allowed because there's a very small mixing with this singlet sigma, this asynchronous state. Okay. And that would then allow us to tune alpha parallel without actually affecting alpha perp at all. So we should be able to go into this transition, tune one of these polarized abilities and not affect the other. And the idea is that we just tune it, we tune alpha parallel to be equal to the background value of alpha perp, and then alpha 2 goes to 0. And so, sorry, yeah.
Feel that point, but if this is the case, if you're tuning alpha parallel, then they should be like you are going to a pi.
I'm going to a pi, but I'm going to a triplet pi, which is weakly mixed with. So I'm actually driving the singlet sigma component of this transition.
And that's how you affect that.
And that's why it's affecting alpha parallel. Yeah. Because I can't the triplet pi bit is forbidden. So I'm actually driving a transition to this very weakly mixed component of this sigma. Okay. So we worked with Svetlana on this, and she did some calculations, and so this is what we expect to see for the polarizability of the molecule. This is now for the rotational ground state and the first rotationally excited state is a function of the tuning, and each one of these poles is a vibration pole in the molecule, so we're hitting a different vibration position. And the nice thing is that line width is expected to just be from the theory of about 15 kilo. Very narrow line width transition. And so if you zoom right in, you resolve some rotational structure. Okay. And you start to see, so these plots are for rotational ground state, first rotational excited state with two different polarizations, and you see crossings. Okay. So the crossing here, where the polarizabilities are the same. And this was used in MPQ. I want to stress, this is not alpha 2 equal to 0, right? There's still an angle dependence here. This is just a crossing. It's not, we've not tuned the anisotropic polarizability to 0. But if you look further out, actually between these vibrational poles, so this scale now is 1600 gigahertz, there's a crossing in the theory tuned by 220 gigahertz or so. I want to stress that is a long, that's far detuned. Because the line width is only tens of kilometers. So don't be put off and say, we're close to the line, we're far detuned. And here we have this crossing, and now in all polarizations cross. At this point, we tune down to 2 to be 0. And from the slope, and you put in the numbers, you say, well, let's say I stabilize the laser line for 100 kilohertz. Typical trap, I should be able to get 13 seconds coherence times on n equals 0 to 1. I don't know what the current record is, maybe the record is in the teaser, and it's a whole hundreds of minutes. So this should be fabulous. And it's even better than that, because we've tuned out to be 0, and we far tuned from the rotational structure, the polarizability of all the rotational states more or less crosses in this region. Right. The polarizability of the first 5 rotational states only differs by 0.1%. There's nearly magic for many rotational states at once. So can we do this? So we got a laser. There's not very much power. It wasn't enough to track, but we could have this like a spectroscopy, the microwave spectroscopy. So we thought we'll do the spectroscopy and see what we see. And we're doing the same kind of microwave transitions, looking at how the line is shaped. So we can map back what Arne calculated. So this is like a core scan, seeing these poles. You notice associated with each vibrational pole is this magic detuning. And we measured it to be 185 gigahertz, the recipium, I think, and which wasn't a bad reading with the data. Then you can zoom right in and actually do a very fine scan. So actually we made the laser much more intense and did a microwave transition now, and we're looking at the shift of 2 different laser polarizations. Okay. And this is the free space line. And this is when you get excited, because these 2 lines cross at exactly the same frequency. They cross the free space value at exactly the same frequency. But here we have no angle dependence at all in the transition, which is evidence that the anisotropic polarizability is tuned to 0. And we can do that for a different state in the molecule, drive a different transition. This one shifts in the opposite way, but they still cross at the same place. And we can do it for all kinds of different transitions, right? So the red and the green are from 0 to 1. The blue is from 1 to 2 in the molecule. The golden color is from 2 to 3. And they're all intersecting at the same detuning. What I was saying that this graph is magic for all the rotational states, certainly the lowest. And we did some preliminary gravity measurements. Again, this is not a trap, so there's only 1 millisecond of evolution time, and we can map this out, and it looks great. But what I want to tell you though is, let me address a concern first. Okay, so the concern is maybe you're going to scatter lots of photons because you're close to a transition. But I think emphasize it's not really close. Right? The transition line which we can measure. So this is the line which we're exciting the transition. And we can measure that from an AC start shift, and actually we find that the transition line is just 9 kilohertz. And of course, from the excited state, the molecule can decay different ways, different places, and so you expect to have a broader line up there. But when we measure that by measuring the scattering rate, that's only 24 kilohertz. And that's kind of expected because actually the 2 states, the X singular and the feature of the line sit more or less on the feature. In fact, they have been sort of proposed to doing laser cooling in these bi-half-life orbits. So we expect it to be highly diagonal, and it does look like that. So if you put in the numbers, then I think for what we should expect, so a 10 microkelvin trap, we should have 8 second lifetime due to this scattering. So I don't think the scattering is going to. And then, okay, so finally we got a very frustrating trying to get money for a laser to do this experiment. Eventually we got one 4 watts that is long enough to track. And this is just confirming those lifetimes. So this is the lifetime of rotational correct state. The first rotationally excited state. It's about 300 milliseconds. So testing visions. Again, it's the same as we measure in 1064 nanometers. Nothing bad happening due to the laser. So then you measure the coherence, right? And so this is the data that we're taking at the moment. So this is Ramsey on 0 to 1. Okay. And I should emphasize the frequency matters of the laser. Right? And you lock it very well. We're not locking it very well at the moment. The laser frequency is poorly locked. Probably jittered around by like 5 megahertz. But we measure 90 millisecond coherence time on 0 to 1. If we do an add a spin echo, then it increases slightly, but not so much. And so we're wondering what limits the coherence, and actually I think it's probably dipole. Our molecules are randomly distributed in the cloud. When we prepare this superposition, of course, we're preparing oscillating dipoles that then interact with one another, and all the distance is different, they all have different interaction strengths. If you do the back of the envelope calculation, you come out with a number. So can we do an experiment? And the experiment we can do is actually do a superposition of n equals 0 and n equals 2, right, where there's no dipole. Then this coherence becomes longer. It's messy because we're not locking the laser frequency very well. But we can do a spin echo on that. And that's what we measure. We then measure these green lines. Okay? And so now we have a superposition of 0 and 2 with coherence times seconds. Right? So we're very excited by this. I think this magic trap will solve lots of problems for us. And this is just showing the fringes that we measure out at 700 milliseconds on this 0 to 2.
So you can introduce the that now in the controlled way by adding.
Well, I can introduce it by adding an electric field and kill the coherence.
How do we kill?
Well, I think it's the noise on the electric field. So we will introduce it in a controlled way by adding it. Yeah.
So you tuned the magic trap for n equals 0 to 1. How good is it for n equals 0 to 2? I mean, obviously it's good, but
That's a good question, actually. So there is a slight tweak in the frequency on the order of, I think it's like 100 megahertz to go magic from to 0. Yeah. Yeah.
What concentration of the laser
The phase, I think we've not really analyzed this yet. I think there's probably something slightly off in the timing of the sequence. But actually there's a very nice quadratic shift of the spin echo fringe. But it's something I think to be understood. Yeah, this is as I said, data from literally last week, and I just wanted to share this because I think it's the first time really we've seen the rotational coherences go beyond the second.
Well, I think two things. So with spin echo and without spin echo, with spin echo is it mostly taking care of simulations?
It's mostly taking care of the fact that the laser
Oh, is it zero? Oh, I see. It's
jittering around from shot to shot because we don't have a good reference at 1146, so we're doing this scanning cavity transfer log, which only updates like every 20 seconds or something. It's just not very good, and actually the cavity itself might be drifting. So, but that we can sort out. Order the cavity, and we'll just lock this to a cavity. We'll have 1 kilohertz stability on this, then that will go away.
I'm just curious, for the, black and blue curve, this is to use the natural thing, but for the red.
Yeah, so we visited the other curves with a Gaussian, following what they've done in the tweezer experiment. So, yeah, it's work in progress, but it didn't seem sensible to fit an explanation because it's basically flat. Yeah. But yeah, I think the take-home message is this: this is really probing what coherence you can get in this flat. Okay, so the outlook associated with this is we do want to control these dipole attractions. We want to add a lattice, and actually, light is really kind sometimes. So, so what I should emphasize is magic laser frequency has a very weak dependence on the polarization. So you see this doesn't quite cross at the same frequency. Shift is about 200 megahertz. So you can actually calculate the magic detuning as a function of the laser polarization, and it has this dependence. And the experimental missiles recognize these kind of numbers. These are kind of standard AOM frequencies. What it means is for a 3D lattice, we can actually have the 3 lattice beams have different frequencies, but all of them independently be exactly magic. So we can make an exactly magic 3D lattice with this technique, and that's hopefully going to enable the thing. Are there any more questions on this? I don't know how to do it, but as I said, I'll just carry on. Okay, so I just wanted to kind of wrap up with a little bit of an outlook about the fun things we're doing in tweezers. And Cancun has explained this, and she is the pioneer of this, and we thought it was so great that we thought, oh, okay, we need to do some of that as well. So the idea is you load your tweezers with your atoms, you pull them to the emotional ground state, you put them together, do magneto-association, then you do stirrup, you get a ground state molecule, ideally in emotional ground state tweezer, with single molecule, which we could find in experiments. Demon dreams of that. So we built this, of course, using our favorite molecule for rubidium cesium, and this is exactly like the diagrams of Cancun shown, and we can load atoms in the same way. And it seems obligatory actually to make your local lab bar. And so if you've never been to Durham in the Northeast, there's this Anthony Gormley statue, which is an enormous, many meters high statue, and so that's our rendition of it at like 50 microns high. And we've done the sideband cooling to the ground state, the details in this paper, but there's nothing really revolutionary about that. And then we started to want to make molecules, right? So we merged the 2 potentials, and actually for technical reasons, we then transfer them into a 1065 trap. And then we want to start magneto association. And so this is a slightly complicated sequence. So this is the flashback resonance we're going to sweep across is that favorite one at 197 Gauss. And we do 2 experiments. So this is the emphasize this need to be in the emotional ground state. So first of all, if we sweep across the resonance the wrong way, that actually promotes the atom pair to a higher motional state of the tweezer. So then you'd expect when you sweep back across that you wouldn't form a molecule in this case. But if we do the experiment coming from the other side, and we prepared it in the motional ground state, then we should, when we sweep across, rather than just going down motional level, we should actually couple it to the molecular ground state. And that's the measurement we did. Okay, so there we're sweeping across with this motionally excited state, and we don't see any signature of the resonance. And then when we sweep across, we see the association with the molecule. And this is just exactly what's Aquinas shown. Let me remind you, so what we're expecting to happen here is to sweep across this this resonance and then follow this red line down, just as we did in the bulk gas experiment. And so we started doing these experiments, and we were just totally confused as to what was happening. Let me try and explain why we were totally confused. Because we've unpicked it. So we can probe what band state we're going to by shining on our pump laser 1557. It's the one we use for Stiro to drive a transition. And for some reason, we kept ending up finding we found this state, right? We swept across this resonance, or so we thought. And rather than following this blue line, we kept following this red line. And we were going into a completely different molecular state, and we were very confused about this for a long time. And then we found this old paper, 20 years old, by Ivan Deutsch, who explained that you could get what he called a track-induced shape resonance. And so the picture is this, that I have this molecule, this one atom, which has a bound state near threshold. That's the molecular bound state we want to couple into. And when you bring a tweezer close to that, so this is the tweezer potential, say, that raises up this potential associated with the interatomic interaction. And it can raise up this bound state to the point where it has the same energy as the lowest state in the tweezer. And then there's a small barrier, and you can get coupling across this. This looks just like a shape. We do some calculations of that. So now this is now looking at the states in the system. So this is the molecular state, this red line, and it's shifting quadratically as a function of the separation of the tweezers, because just because of that potential raising up the molecular state. And then these are the separated motional states. And because of this shape resonance, you get an avoided crossing here, okay, as a function of the separation of the tweezers. And you can estimate where that sits, and it requires a large scattering, a large background scattering. Bound state has to be near threshold, otherwise this happens far apart and the barrier is just too wide that you don't get any thunder. But we have a large background scattering, it's within CDM, so it has this large scattering length of 34 nanometers. So what that means is we get an avoided crossing here, which can be tens of kilohertz, and it depends on the confinement strength. But in a tight tweezer with reasonable confinement, you get an avoided crossing, which is broad enough to follow adiabatically. So the idea is you just sweep. When you bring the tweezers together, you follow this avoided crossing and you go directly into the near threshold bound state without going across a threshold. And if you think about it, actually that explains what's happening here. Right? So we're merging the tweezers of the field above the Feshbach resonance, and then when we sweep down, we follow the avoided crossing here and go down here, because we've already populated the near threshold bound state just by merging the two tweezers together. And we can show that we understand that, so we can probe it. So these are the spectra. This is this 1557 nanometer transition, and we can resolve the two states, the blue state that I showed on the previous diagram and the red state. And if we change the confinement, we can switch from doing magneto association to merger association, and call it, right, associated with this merging for the potentials. And actually, it's more or less the same efficiency as magneto association. it's just a little bit harder to control, I'd say, but, so this is kind of puzzled us for a while, but I think we're going to get this, and it's, I think, some nice physics associated with this time confinement. This is just to show that now we have ground state molecules in this system. So, I mean, this bit is straightforward. It's just the same as I showed before for bulk gases. And the nice thing is, so this plot is showing repeated stirrup. Okay, so we measure the pair survival probability as a function of the number of stirrup pulses. So if we go one way, then obviously we don't see any atoms survive. If we come back, we see them. We go again, go back, go back. And so this is a function of the number of pulses, and then see this decay for a pair survival probability, and that's just measuring the efficiency of stirrup, which we get exactly the same, 91% efficiency, the same as we get in bulk gas. So what we're doing now is this idea of combining Rydberg atoms and molecules. And Frank talked about the nice work she has on this. Some of the students have worked on this. So to use a Rydberg atom to engineer strong gates between molecules. The nice thing here is we have atoms. We've already got the atoms of the tweezers. So we've started a project with Hussein and Rosario to look into this. And at the moment, we're exciting to 52S in the rubidium level. And then the charge dipole interaction between the molecule and this Rydberg atom leads to some potential. What Rosario calculates for us looks like this as a function of the separation of the atom and the molecule. So the shifts are big, but you really do have to get quite close, right? You actually have to get to about 300 nanometers or so to see this effect. But if we did that, we should see blockade. Right? We should blockade the transition. And that's exactly what we see. So this is Rydberg, driving Rydberg gravity oscillations now up to 52S. The green is when there's no molecule present, and we see gravity oscillations. And then when we have a molecule in a tweezer, ground state molecule, around 300 nanometers or so away from the Rydberg atom, then this transition becomes blockaded. And this is just showing kind of spectra that we see for these two cases. This is 800 nanometer separation, and this is 300 nanometer separation. You see this suppression of the transition due to this Rydberg atom molecule blockade. So I think this is the first step towards what we'd like to do is make these interactions resonant, find the right Rydberg level, make a much stronger interaction, but this is already, I think, very exciting for us to see this interaction between a single Rydberg atom. So I really should stop, I think. There's lots of future challenges that we're working on, not least to get something like lattices working, turn our magic trap into the magic lattice, and start doing really long simulations with the molecule that way. So I should really thank all the wonderful people who do these experiments, it's these guys, and the theorists who helped us along the way to understand what we're doing. And whoever wants to come to Durham, very well. Okay, so let me stop there and have any questions.
That's interesting, the last one, the molecule.
Yeah.
So how do I think about the Rydberg atoms here, I guess?
Funny, think of it like that.
Yeah, it's like this electron is outside.
Yeah, so actually, so what, I mean, the same can explain more, but what you're seeing here is when the molecule is coming into the outer orbit of that Rydberg electron.
And you, when you do it, do you turn off the tweets and track?
In this case,
Or it's so short?
I think we leave it on, actually, yeah. Yeah. The limitation here is how, we do have to get to like 300 nanometers. And slightly more, the atom tunnels into the same tweezer as the molecule. And then those pesky collision. Everything's gone. Sorry, Jack. I know.
I'm not responsible for those collisions. Neither.
Yeah. So, yeah, so, I mean,
But in terms of optics, is there a limitation? I mean, that's pretty close, right? Or they're
the
just
tweeters are totally overlapped,
Yeah.
right? But
Oh.
they're a little bit, they're not perfectly, but they're almost species specific. So the rubidium is in 817 nanometers, which turns out to be almost, not quite, but close to zero polarizability molecule. The molecule's in 1065, which is quite high polarizability of the molecule, but low rubidium. So that's how we can bring them so close together. We don't see it do that. Yeah. We've also done a lot of measurements where we turn, maybe we turn off the tweezer. I need to check because it's a very deep result. But yeah, I think obviously the time scale here is just microseconds. So we can actually turn off the tweezer and just do this experiment and everything's frozen. I should say with the atom is also cooled to the motional ground state of its respective tweezer as well.
But that probably doesn't matter.
It probably doesn't matter, but we have that free. We were doing it for the molecule.
Any other questions?
We'll take a 10 microsecond break. It's a typical Richard lifetime.
It's the bad.
I should close the Zoom on here.
Yeah, yeah.
Yeah.